All right, gang, MATH6500. Going to demonstrate in this video, or maybe this video may have to be split into two or three because there's a lot going on. Something called an F-test for lack of fit. And essentially what I'm going to try to teach you in these videos is a formal procedure that we can use to determine if a linear model is appropriate for describing the relationship between our x and our y. Assumptions remain the same, nothing new here. We're still assuming independence, normally distributed errors, and equal variances across each level of x. Now, interesting caveat, and this kind of annoys me, but it just is what it is. As you see the process unfold, you'll see why this is a critical assumption that we have to meet. So to implement this F-test, lack of fit, we have to have repeated values of y at one or more levels of x, called replications. So the data set that we're going to use, or I'm going to use in this demonstration, is called ACT nonlinear. Might tell you right off the bat that we're dealing with a relationship that is nonlinear. I chose that purposely. I didn't want to demonstrate this in a situation or case where a linear model was appropriate. I want to demonstrate the opposite of that. So we're working with a nonlinear model, as you'll see, but I want to show you how the process plays out. Because oftentimes it's a difficult decision. So anyway, we start out by fitting a linear model, linear function, just as we've previously done. And the data set that I have already installed in R is called the ACT nonlinear. And you can see that the independent variable would be ACT, the predictor, and the response or the dependent variable would be first year GPA. Now, you can see that what the first thing I did here is I created a table of ACT because I need to check that I have at least one level of x where I have a repeated value. And you can see here that we have 6 ACT scores, and all of them have repeated values except for the ACT of 26. There's only one 26 included in the data set. All right, so the first thing I do is I create a model, and you can see from the coefficient estimates that this is the way that we get this here. Okay. Now I really don't know why we start out, because we really don't use this model much. It's pretty strange. In fact, I'm trying to think the process through. I don't think we use it anymore at all. So. But anyway, it's a very interesting approach at determining if a linear model is appropriate. Now, let's just dive into the relationship between ACT and first year GPA. The first thing I probably want to do is just look at a scatter plot of ACT first year GPA, and I'm going to include the regression model. So you can tell that we don't have a linear function. A linear model does not fit our data well by eyeballing it. Another thing that we could do is we could look at a plot of our fitted values for our model. So look at the residuals over the fitted model. We get that kind of reverse U. So problem areas with the scatter plot and the residual plot. So we're thinking now that through eyeballing the plots that we do not have a relationship that should be modeled by the linear function. But what I'm going to give you is a much more formal procedure by which we can test that. All right, so here's the way it plays out. First thing we'll do is we'll create a new data set using the mean of the y's for the x's with replication. So I've already done a little bit of that. What I did is, first of all, from the table, I see that I only have 6 values, 16, 19, 23, and so on. So I created something called XC. You can see that C in our notation deals with the number of levels we have at which we have repeated measurements, or a single measurement as far as that goes. So notice here again is C is 6 because we have six scores, 6 ACT scores. A little bit more notation. N is just the sum of the n sub j's. So the n sub j for x1 would obviously be 2. The n sub j for x2 would obviously be 2 from what we saw above in our table. All right, so the n sub j for j equal 4 would be equal to 1. So, and again, we run that all the way up to 6. Now we're going to begin the general linear test. So what we want to do here is we want to create a full model where we look at we express the y values as the mean plus an error term. So what we have here is, again, the means are the mean of the y's at that particular value of j. So what I've done over here is I've created the means of y's. So now how did I get 1.695? Well, if you look at 16, 16 has a 1.6 and a 1.79. It only has 2 measures, so I just added those two, divided by 2, and got the average. Same thing for a score of 19. 19 had 2 measurements. What were they? 3.05 and 2.73. So the mean of those 2 scores is 2.89. So what we're saying there is that the y values up here, each of these y values can be expressed as the mean plus or minus an error term. So we create a new model, right? It's called the full model. Here the n sub j's have parameters, again, j 1, 2, 3 up to c, and the errors are independent and normally distributed with mean 0 and variance sigma squared. Since our error term has mean 0, then we know that the expected value for the y sub ij must be the mean of at that particular j level, right? So again, this j, just so it's clear, because it's extremely important. 16 would be j equal 1, 19 would be j equal 2, and so on and so forth. Now, the full model, just like any model, is made up of 2 parts. It's made up of our mean response for each of the x sub j's and a random error term. All right, now what's the difference between this full model and a typical regression model? Full model is we have no restrictions on our mu sub j. They're not linearly related. Easy for you to say. Not necessarily linearly related to the y's. But the regression model, we of course have our expected value for y as a linear function of some intercept and some slope. All right. So at the end of the day, drum roll please, the mu sub j, the predicted value for the mu sub j, is just the mean of the y values at that particular level j. Now, I'm going to move into some important calculations next. The first thing that we need to create is called the sum of squares for the full model. And there's a few places I think that I call this sum of squares error for the full. We ultimately end up calling it SSPE, which is just the pure error sum of squares, or the sum of squares for the pure error. So in other words, it plays a critical role in the lack of fit. again, we kind of assume we have a linear model. We create this other model that examines the lack of fit from the linear model, the base model. So this is a pretty easy calculation. We're doing double summations, so we run through all of the j cases. In this case, 1, 2, 3, 4, 5, 6, and we have all the i's. So we have y sub ij minus the mean of the jth term. So in other words, what we're going to do here is all of the y's for j equal 1. We're going to take the first one, subtract it from the mean for the j's, square it. Take the second one, subtract it from the mean for the j's, square it. And I think that it's going to be much clearer on the next page. I mean, that should be relatively clear, but I think it'll be clearer when we start looking at the numbers. So essentially, this SSPE is the sum of squared deviations at each x level. So for x1 equals 16, notice we have a y of 1.6. Again, the mean, let me go over here. The mean of the 16s is 1.695. So one of the GPAs at an ACT of 16 was 1.6. It is that far away from the mean for the ACTs of 16. And then we have another GPA of 1.79 minus the mean. So we're looking at the deviation squared. For 19, we have 2. Notice for x4, 26, we only have 1. So this really is irrelevant in terms of its contribution to the SSPE because the only value we have is obviously equal to the mean. And if we get to x equal 32, or I'm sorry, x6 equal 32, we'll see from our original data set that one of the GPAs is 2.89 and the other GPA is 2.62, and the mean of the y's at for 32 is 2.755. So if you sum all that up, which I did right here, it was a royal pain because it was tedious work. Yeah, so afraid of a typo. So you can see that the SSPE in this case, or sum of squares for the pure air, is 0.20795. Now it turns out that the degrees of freedom for this particular sum of squares is nothing more than n minus c. So we calculate that by summing the sample sizes over j, subtract 1, which is equivalent to taking the sum of the n sub j's minus c. Because if we have 1, 1, 1, 1, 1, we have our c, which is 6 in this case. So our total sample size is 11 minus 6. Our degrees of freedom here would be equal to 5. Now I will say, again, the calculations here are kind of tedious. I don't think this is a video that you can like put reruns of The Office and Friends or whatever, and simultaneously watch this video. I think it's going to be something you're going to have to really pay attention to the detail. All right, now we're going to switch gears to the full model. Actually, from the full model to the reduced model. So under the null hypothesis that the expected values for y can be expressed as a linear relationship, meaning what? If we fail to reject the null, we can assume that a linear model is appropriate for describing the relationship between our x and our y, not our xc. Right? I'm talking about our original data set of ACTs and GPAs. The alternative is that the expected value is not expressed by a linear function. So we'll play it out. H sub O claims that mu sub j in the full model is linearly related to the x sub j's. In other words, we can rewrite mu sub j as equal a linear function of our x sub j's. So the reduced model under the null hypothesis would be that each y sub ij, so each y we have in our data set, all 11 of them, can be expressed by a slope and an intercept times the x sub j plus an error term. So this is nothing more than the regular simple linear regression model recognizing our replications. So in other words, we're going to run a second model based on our XC's and our mean Y's, and then we're going to compare the full and the reduced models to determine, again, if a linear model is appropriate for describing the relationship. All right, so I think everything's pretty clear so far. Now we'll dive into the reduced model. Now again, the reduced model, the beta coefficients here, coefficient estimates, are going to come from the model that we create from our repeated values. So what I want to do here is I want to create, I'm just going to call it the C model, since the C stands for the reduced model, if you will. And I am going to take the linear model and I'm going to predict the mean Y from the XC. Okay, what did I do wrong? Oh, okay. And we can do summary of C model, and we can get our coefficients. Notice our coefficients are, different. Not a lot different, but they are. The slope before was 0.053, and now it's 0.054. So not a lot of difference. So when we look at our reduced model, what we look at is we look at expressing our first Y. So I1, J1 for our first level of X plus an error term. So in our data set, let me go back up to it, we can see that the first ACT is 16, and the first observed Y for 16 is 1.6. So we're saying that this relationship right here, using the model that we just created, will fit true with a specific error term. The second, Y sub 2, 1, using the same model, again, same X level because we have two of them. And we notice that the X level is still 16, and the Y that goes with the 16, the other one is 1.79. So again, that relationship can be expressed using the beta 0, beta 1 estimates from this new model that we've created. And when you get down to the very last one, this will be the second Y from the sixth level. Again, the second Y from the sixth level, so that would be 32. Hence the 32 here. And the second one would be our 2.62, right? So again, we can express that relationship the same way. All right, so generalizing a little bit, we could say that Yij is equal to B0 plus B1 times Xj. Again, just focusing on the levels, and plus an error term. So in other words, we know that we can predict Y sub ij by just this relationship. So clearly the sum of squares error for the reduced model, which I call SSE RED, is going to be exactly like we've looked at sum of squares errors before, right? Observed minus predicted. This is very sloppy right there. So we're going to sum over J's and I's, and we know that this is the predicted value, right? So we have the sum of squares error, just as we've seen it many, many times before, as the sum of the deviations of the observed minus the predicted. Now, to calculate this, we need to create our model. So if you focus on this model, you'll see where I got it from. So 1.52265, and then 0.05441 is the slope of that model. But, and this is where I see a lot of mistakes made, and I almost made it when I was creating this video, or getting prepared to create the video. We calculate the errors for each y from the beginning data set using the reduced model. So anyway, that's a mistake that I almost made. So we're going to have 11 cases instead of just 6 using the means. So we will dive into the very first case, which has x value of 23, right? An observed value of 3.38. So we can predict this value at ACT equal 23 by taking the observed minus the prediction squared. The second case, of course, has a y value of 2.73 at a level of 19. So again, we're predicting using this reduced model. And we do this for all 11 cases. So once we add all these up, I end up getting 2.608 as the sum of squares for the reduced model. And this is a tedious calculation. I didn't want to do this in a video because it took too long. It took me probably 20 minutes because, again, I was so afraid of creating a typo. So now we switch gears to calculating the test statistic. In this case, we use the F distribution, and the F statistics turns out to be the sum of squares for the reduced model minus the sum of squares for the full model, divided by the difference in the respective degrees of freedom, all divided by the sum of squares for the full model divided by its respective degrees of freedom. To be consistent with notation, I called this SS sum of squares error for the reduced model, and earlier I referred to the sum of squares for the full as SSPE for the pure error. It turns out here, this is actually, I believe, n minus 2 minus n minus c, right? So you can see that n minus n, and then of course a negative makes it c, so this is where I get to c minus 2. I should have explained that clearer. And then over here we just get over n minus c. So plug and chug now. 2.608 minus 0.208 over 4 degrees of freedom. And I wrote this out. I typically wouldn't, but since I'm teaching, if you get down to where you don't get 14.42, maybe this will help you identify your problem. So the next thing I would do is use R to calculate the p-value. I've already done that, but let me demonstrate it. So remember, the p-value for an for the F distribution is just the area to the right. So it's in the right tail, right of the test statistics. So I need to subtract it from 1 because PF will give me the area below. So I need 14.42 degrees of freedom for the reduced, I think was 4, right? Yeah, and degrees of freedom for the full, or SSPE was 5, yeah. So you can see that the p-value is 0.006. So if we, let me go back into my notes here. And hopefully find the null hypothesis. Yeah, here we go. So what we would do is we would reject the null because our p-value is less than 0.05. So we would conclude that the relationship between x and y cannot be explained by a linear function. Now, sometimes people throw in the towels and they say, well, there's no relationship between x and y. That's not true. We're not testing just a global, broad statement as there's no relationship. We're testing the relationship, if there's a linear relationship that describes the relationship between the two variables. So, huge difference. All right, so let's define a new term, one that helps quite a bit in the calculations. You might say, why didn't you tell me that earlier? Well, I don't know. Let's proceed. So let's define the sum of squares for the lack of fit as SSLF for obvious reasons. And we can define SSLF as being the difference between the sum of squares for the reduced model and this SSPE that we defined earlier. So, simple calculation, if we know SSLF, the sum of squares for the lack of fit, we can just put it in the numerator. Degrees of freedom stay the same. And in the compound fraction, the denominator stays the same. So when we have a sum of squares divided by its degrees of freedom, we refer to that as the mean square. So this would be the mean square for the lack of fit, and this would be the mean square for the pure error. So that's technically what the F statistic is. And you'll find that I think calculating the sum of squares for the lack of fit is an easier calculation because we take, again, double summations. We take the mean of the y at each level minus the predicted value of each value, and of course square the deviations. And this all simplifies to just being n sub j times the mean of the y's at the j level minus the predicted value at the j level, since all these fitted values of x are the same. All right, so that eliminates the need for the I sub j, sub ij, I should say. Okay, I didn't remember doing this, but I was thinking I wish I did. So I do a calculation for you, and again, if we think about what we have here, so we have by the way, it should be a summation there over j. So again, if we have a summation over j of n sub j, y bar sub j minus y hat sub j, quantity squared. So it works out nicely because we only have to make 6 calculations because we're summing over j. Again, j was 1 to 6. So our multiply by 2 because we have 2 responses in for what j equal 1, which I believe was ACT equals 16. So the observed value was 1.695. The observed mean response, right? And then the predicted was negative 2.393, which we could easily find using the, let me demonstrate that. What we could do is we have our C model, right? So what I could do is I could do the predicted values. Let's do predicted C's just to be consistent. And what I could do is I could take the 1.52265 and plus 0.05441 times the XC's. All right, so the 2.393 that I get right here is just the predicted value that we get for x sub c equal 1, if you will, which of course is an ACT of 16. Now, when we make those calculations, again, I did this previously because this is all. Arithmetic is stressful for me. I don't know about you. I'm always afraid of doing something silly and transposing numbers or typo, whatever. So anyway, I'm pretty sure I got this correct because it is 2.401, and of course we have a relationship where the sum of squares is equal to these two components. The partial error plus the lack of fit is the total sum of squares. And of course, we saw previously that the partial minus the full was 2.4, which matches with what we have right there. And again, let me put this in proper context. That is this part right here. So this can be replaced with sum of squares for the lack of fit. All right, guys. About done. So what in the heck have we done here, right? So this sum of squares lack of fit measures the lack of fit because it compares our fitted values and our means, right? So again, let me bring this back so we can get a visual. So it compares these two values. Well, if your fitted value and your mean value are extremely close, then this quantity is going to be very, very small. And if you sum up a bunch of small quantities, well, you're going to get a small test statistic, which is going to create a high p-value, which is going to lead to not rejecting the null, right? Again, if we go back over to the null hypothesis, it's going to lead us to not reject this null and conclude that a linear model is appropriate. On the other hand, if we get to this calculation and there's a large difference between the mean at each j level and the predicted value at each j level, then this is going to be a large quantity. And if we have a lot of large quantities that we add up, then we get a large test statistic, which creates a low p-value, which in essence is strong evidence against the null hypothesis. And in this context, strong evidence against the null hypothesis is strong evidence against a linear relationship being the appropriate model to describe what's going on between x and y. In this case, ACT and first-year GPA. All right, so that's really what's going on. That's kind of what I just write out right here, so you can take a screenshot if you like. So finally, maybe worth noting why are the degrees of freedom for the lack of fit sum squares error for the lack of fit C minus 2? Well, because we have C means and we lose 2 degrees of freedom because we have made an estimate for beta 0 and beta 1. Specifically B0 and B1. So C minus 2 is the degrees of freedom for the sum of squares lack of fit. All right, gang, so all I got. Again, this is a really cool approach that I don't think you see a lot, but I think it's very, very helpful when we're trying to assess if a linear model is appropriate for describing a relationship. And there's another caveat where the box is checked where we have X levels with repetitions. So, all right, that's all I got. Take care.